Very good morning, children. So we'll start our last session for the dual nature of radiation. So as of now, just one second. So as of now, we discussed the dual nature of radiation from last 4 classes. Okay, just quickly revise what we discussed in the last class. Okay. So in last class we discussed about dual nature of the radiation. So dual nature, in that we discussed about the particle nature, and so meanwhile we discussed the photon structure, properties of the photon. Then we discussed about the de Broglie waves. So that is nothing but matter waves. So then what is de Broglie wave? How we derive how the de Broglie wavelength we derive from. Okay, so that by using of Einstein equation and quantum theory. So we derived the lambda value, and then de Broglie wavelength for the particles like electron, proton, deuteron, okay, and alpha particles. So these equations I given in last class. Okay. Now coming to the last topic. As of now, we discussed about the dual nature of the particle or matter waves. So matter waves are nothing but the particle which are moving, which are having a mass and moving in a beam. Okay, that shows the wave nature. Okay, like electrons. I said that electrons, protons also having mass, and when it moves from one point to other point, so it shows the particle nature as well as wave nature. Okay, this we know. Now coming to matter waves shows the wave nature. So it's showing wave nature. So definitely that waves has some wavelength. For that wavelength, how to find out the wavelength? De Broglie given one equation, that is lambda is equals to h by p. So the 2-3 forms have already we discussed about it. Okay. Then practically, so saying one statement is not every time is not worthful. So we need to prove that statement. So then only it will be worthful. So then how to verify? Okay, how to verify? How to show that? So but electrons, the flow of electrons have some wavelength. Okay, and that is the wave nature of radiation. So experimentally verification of wave nature of radiation or electrons. Okay, so that experimentally verification done by Davison, Germer and Davison. Okay, so by using one apparatus, by one electron gun, by applying of high tensions and some heavy target like nickel crystals, by using movable microscope or galvanometer. Okay, so these they done an experiment. So I will discuss that experiment. That is the last topic in our dual nature. So we'll go for it. Davison and Germer experiment. So this is also called as the experimental verification of dual nature or wave nature of light or wave nature of radiation. The experimentally verification of wave nature of matters or matter waves or electrons, you can take it. Okay. So what are the operators? What it consists of? Okay. First, I like that. So in this experiment we are using electron beam. How to produce electron beam? By using one filament. Actually take this one filament. So which is connected, initially it's connected to low tension. Which is connected to low tension. So by applying of this low tension, this is a source, we call as source of the electrons. So when you are applying the low tension, it got it heated and the electrons ready to liberate from it. Okay. And so when the electrons are liberated from this filament, okay, by applying of some external tension, so these electrons will move in a straight line. So it will move towards the positive charges or positive potential. So here positive potential we are taking here anode. So there is an anode tube which consists of the small hole. Okay, so this we are taking as an anode tube. So the ejected or emitted electrons from this filament, okay, moving towards and passing through the anode in a straight line. Okay, how it is possible? By connecting of high tension. So cathode we are connecting to negative and connected to positive. So this is a high tension we are applied between the cathode or source of ejected electrons and anode. So due to this, electrons are ejecting and it's moving towards the anode. But anode is not a plate; it's like a cylindrical tube. So the electrons are passing through this anode and incident on one target. Instant on one target. And this target is made with of nickel crystal. And this is connected like the atom planes will be along diagonal. The plane of atoms. Okay, or not. So, okay. So this is nothing but plane of atoms. Plane of atoms. Okay. So when the electrons incident on nickel plate, okay, so it will scatter in all directions. Okay, let us assume so it is scattered like this. Scattered in this angle. These are the ejected. So scattered by an angle. Let us assume it is pi. Pi is a scattered angle or angle of scattering. Okay, these electrons. So the scattered electrons are measured by one galvanometer or one microscope. So that is which is placed on a movable scale. Okay, so there is a external circuit here and a microscope. So which is connected to external circuit. So this microscope will count that or measure that how many electrons are coming towards it, okay, or for every second. So that nothing but we can easily measure that how many number of electrons or what is the intensity of that electrons. The more electrons reaches it, more energy, so the intensity also more. Okay, that to find out the intensity, so we are using one scale. Okay, on that scale we are using one microscope to measure it. Okay, this total operator placed in a vacuum chamber. Because we know that ionization, to reduce the ionization effect, the plane of atoms. So this is structure, Davison and German experiment. So what are the operators? First, cathode, that is source of electrons, okay, that's a filament, okay, which is connected to low tension. Okay. Next, anode and cathode plate, which is connected to high tension. So the ejected electrons is passing over the anode and incident on a nickel crystal. Okay, and remaining. So when the electrons incident on nickel crystal, it is scattered in all directions. So like a particular beam of electrons. Okay. So the scattered or reflected beam of electrons are incident on the microscope, which is placed on a movable scale. Okay, which is used to. So this scale we are using used to measure the angle, and to find out the intensity we are using the microscope, which is connected to external circuit. Okay, so this is the experiment. Okay, so how this experiment has done. So this experiment accelerated between the particular potential. Okay, first point. Remember it. So the potential we applied it's also called accelerated potential. What is accelerated potential? So electrons are ejecting from the filament. Okay. So if you give some sufficient of energy, that is some amount of energy, x amount of energy. The x amount of energy, so some few we know that as according to photoelectric effect, when some amount is used to eject the electron and remaining it is converted into kinetic energy. So that's it. So how much of energy? So we are giving. So that is converted into kinetic energy of electrons. So how the kinetic energy will comes by applying due to applied potential between this cathode and anode. Cathode nothing but source of electron here. Okay, negative and anode, positive. Okay, so this total experiment operated between accelerated potential, that is between 44 volts to 68 volts. 44 to 68 volts. So this experiment is done. Okay, so between this experiment is performed between the accelerated potential 44 volts to 68 volts. Okay, point number 1. Okay, so and by every potential, every applied potential. So we need to measure, or the measurement is done, measurement of intensity of the scattered electrons done with different various angles. Okay, if you take this microscope here, okay, so what is the angle of scattering here? It becomes 90. When you take this microscope here, it almost 0. So that means, so we are moving the microscope between 0 to 90 degrees. Between 0 to 90 degrees. Okay, let's see. I am taking it 44 volts. So the electrons are ejecting and passing through the anode and incident on it. So I am taking the microscope initially first. The first reading is here. At 90 degrees, we are measuring the intensity. Because the electrons are scattered in all directions. Electrons are scattered in all directions. Okay. Excuse me.
Wait, why they took me calculate question?
Yeah, you are here?
Asia B.
Now the routes last. Okay, that's it. Okay, see here. So at 44 volts. Okay, we are taking a 44 volts. Okay, we are measuring the intensity at various angles. So if you take the movable microscope here, okay, so the movable microscope and our so scattered angle is 90 degrees. So 90, 89. So by reducing of angle, so we are measuring so total 90 degrees. So from 90 to up to 0 degrees, total 90 values at 44 volts. At 44. Now I am increasing the voltage to 45. Again, this experiment is done between 90 to 0 degrees of scattered angles. So every voltage we are taking the 90 degree, 90 values. Okay. So these everything we are plotting the graph. Okay. Plotting the graph for different angles, a scattered angle and next potential. Okay. If you draw the graph between the intensity of the reflected or scattered electrons to angle of scattering. So it's okay, this one. Okay, wait now. Just see here. So what experiment we are doing? So we are doing this experiment between 44 volts to 68 volts. Every voltage we are taking the 90 value, that is 0 degrees to 90 degrees. Okay. So if you plot the graph between intensity of the scattered electron beam to angle of scattering. So what I say, angle of scattering we are taking from 0 to 90 or 90 to 0. Okay, for different voltages. Okay, what happens in every case? Every case, the intensity increases and reaches the peak value and again decreases. So this is what peak intensity. Okay, so peak value of intensity. So this graph will come, that is intensity versus scattered angle graph. So this graph we have to do for every voltage, 44, 45, 46, 47 up to 68. What the operating voltage is from between 44 to 68. So we should draw the graph for every voltage. What is that? Which graph? Intensity versus scattered angle. So then he concluded that. So what he noticed, what these these scientists noticed. So they find the maximum intensity of scattered electrons. They find the maximum intensity of scattered electron. So that is intensity. Here intensity maximum. They find they observed that maximum intensity of the scattered electron at a voltage of 54 volts. So I said now 44 to 68. So this experiment done in every case. Okay, every case we have to draw between the intensity to scattered angle. At 44 volts of operating voltage and 50 degrees of scattered angle. That is pi value 50 degrees, 54. That means if applied voltage is 54 volts, electrons are ejecting and incident on the nickel crystal. So nickel crystal have different pair of atoms. So it is scattered. So it will not absorb the electrons. So that's why we are using here Adbhuta electron. It is scattered the electrons, heavy metals. Okay, heavy metals we are taking. Okay, when incident on it, so it is the electrons are which is incident on the nickel crystal, the scattered in all direction, all direction. So at 54 volts, that means electron beam is scattered from 0 to 90 degrees. So we are taking the microscope. So at 0 degrees we are finding the intensity, 1 degree, 2 degree, 3 degree, so like up to so on. From 0 degrees to 90 degrees we measure the intensity of scattered electron. But at 54 volts we measure the 90 values or 90 different angle of scatterings, we find the intensity. But at 54 volts, at an angle of 50 degrees, at an angle of 50 degrees, so they observed the peak value of intensity of scattered electron. Okay, so that means what, here operating voltage 54 volts, so maximum intensity outcome here. So then, so these are experiments. Once again here, just briefly we will go through that one. What we take in here, one ton filament, okay, which is connected to low tension, anode. So these two are connected to high tension to give the accelerated potential. So the electric beam of electrons passing in a straight line and passing through the anode and incident on the heavy metals that like nickel crystal. Okay. So then, so which is intersect or which is scattered in form of, it's not along the plane of atoms, it is diagonal along the diagonal of plane of atoms. Scattered like this. Why? Because as you know that in solid states, when so different planes of atoms act as a reflectors. So we will get a different beam of electrons. Okay, beam of electrons from different plane of atoms. Okay, so what happens when scattered electron beam of electrons is scattered in all direction? We are measuring the intensity of the scattered electrons, beam of scattered electrons, by using a movable microscope. Okay, which is connected to external circuit to measure the intensity. Now, so this experiment is operating, accelerating between the 44 to 68 volts. So every voltage we have to draw the graph for the intensity versus scattering angle. So for every voltage we have to measure the 90 values, 0 degrees to 90 degrees, and we have to draw the graph. So finally they observed that at an operating voltage 54 volts. Okay, and the scatter angle at an angle changing from 0 to 90 at an angle of 50 degrees, they observed that maximum or peak value of the intensity of scattered electron. Why the peak value has come? So I said no, the nickel crystal scattered in along the direction, okay, along the diagonal. Okay, the atom planes of atoms is along the diagonal, arranged along the diagonal. When the nickel crystal incident on it, so it reflected from the different planes of atoms. So the two beam of electrons are both are in phase. Both are in phase. As you know that when the waves which are both which are in phase. In phase means what? The phase difference is 0 degrees or 2 pi degrees. If both are in same phase, they form the resonance that we call constructive interference. Due to this constructive interference, the amplitude of the waves are increases. As increasing of amplitude, intensity also increases. That we know that in first year, the intensity of any wave directly proportional to square of the amplitude. Okay. So as increasing due to the interference of the scattered beam from different planes of atoms. Okay. Why intensity is maximum at 54 volts and 50 degrees? So the beam of electron which are diffracted or scattered from different planes of vibration or form the constructive interference. So due to this constructive interference from different waves which are coming from the different planes of atoms, okay, the intensity amplitude becomes maximum, intensity also becomes maximum. So that's why we are observing the peak value of intensity. So they finally conclude that at an operating voltage 54 volts, okay, and angle of scattering is 50 degrees. So the intensity of the scattered electron will be maximum. Okay, so they are given the statement. Okay, so then how this how to find the wavelength? Okay, let's jump into next point. So this is a diagram one, just already explained. Now coming to how they verified. When we observe maximum intensity, maximum peak value intensity at a voltage 54 volts at an angle of scattering 50 degrees. 50 degrees. As we know that the wavelength. Okay, so in last class we discussed about the wavelength of the scattered electrons or wavelength of the electrons. Lambda E is equals to 12.27 divided by root V. If you see the previous notes, you will come to know that one. So this is the wavelength of electrons. So here we are using the electrons, and what is the operating voltage? 54 volts. By substituting all this, so it is an angstrom 12.27 by root 54. Root 54. So by solving of this, you will get the value is equal to 1.65 angstroms. 1.67, near to 1.67 angstroms. So this is experimentally we calculate that the wavelength of the electrons, beam of electrons. Okay, and this value, this is an experimental value. Okay, it's not theoretical value, but the theoretical value of the electron beam 1.65 angstroms, which is almost equal. So that how to find this theoretical value? So there is a one equation, that is Bragg's law. Okay, so 2d sin theta is equals to n lambda concept. So this is not in your syllabus. Okay, so in competitive point of view, we should discuss about it. In chemistry also, in competitive point of view, this question will come in solid state. So this also is called as Bragg's law. Okay, where so theta is the angle of Grace angle, we call as Grace angle. So that is another topic which not belongs to here. The finding of theoretical value by using of Bragg's law for that nickel, which are coming from the nickel crystal. So that lambda E value is equal to 1.65 angstroms. Okay. So but experimentally what we got 1.67 angstroms. So finally they conclude that so the electrons have the wave nature because the wavelength of the electrons is equals to theoretical value. So finally they conclude that the experimental verification of electron or wave nature of electrons. So sometimes you may get the questions. So what is the who proved that wave nature of the electron or wave nature of the radiation experimentally? Davison, Germer. Otherwise, what Davison and Germer proved experimentally or verified experimentally? So wave nature of radiation. So these are the questions. They may ask for 1 or 2 marks. Okay. So this is about our complete topic. So dual nature of radiation. So quickly revise. So what topics we discuss in dual nature. Okay. So just if you have notes, just to go through that one. Just I'll go through. Then we will go through the numericals. How to solve the numericals in this chapter. Then we will discuss that. Okay. Now coming. So what we started here, dual nature of radiation, completely we started with some concepts. Emission of electron, how electrons are emitting, thermionic emission, field emission, photoelectric emission. So that we discussed, and meanwhile we discussed about the cathode ray properties. Cathode rays are nothing but beam of electrons. Okay. So cathode ray properties, then emission of electrons, okay, and source of emission. So in that we taken only photoelectric effect. What is photoelectric effect? Who given height is proposed it. So then Halvich and they done experiment with UV lights. Okay. So this photoelectric effect shows by alkali metal in presence of visible light. So UV light. So UV light also shows the photoelectric effect for normal metals. So in presence of visible light, only alkali metal shows the photoelectric effect. Why? Because the work function of the alkali metals is very less when you compare to other metals. Okay, so that alkali metals. So then photoelectric effect, and then we discuss some observation of photoelectric effect. Okay, and Einstein observations. Okay, the Halvich and Hertz observation regarding it. Okay, so So detailed information you get from NCERT, but briefly we discussed in lab classes. So what is photoelectric effect? Then photoelectric equation. Okay, photoelectric equation. Meanwhile, some parameters we discuss. What is the threshold frequency, threshold wavelength, work function, and stopping potential. Okay. Then stopping potential to kinetic energy relation also we derived it. Then photoelectric equation. Then Einstein given that photoelectric equation. Okay, for experiment. Okay. Then how Milgauss modified that experimentally, Einstein equation by using of stopping potential. Then we see the graph. Okay, and different graphs. Okay, stopping that is anode potential to stopping potential. So frequency, different intensity, different frequencies. So graph we discuss. Our photoelectric current to anode potential graphs we discuss. Almost 4 graphs we discuss about it in the topic. Then we forward to then wave nature. So before wave nature we discuss about the photon structure. So that is particle nature. Then wave nature, de Broglie wavelength. So de Broglie wavelength for the different particle like electron, proton, deuteron. So alpha particles. Then experimental verification of wave nature. Okay. So these are the topics we discuss. Okay, as of now, total 4 classes, and this is the 5th class. Now, what is important for competitive as well as PU examination? So PU examination point of view, don't follow the weightage. Please read each and every question. This gives knowledge. It's not for only marks. Don't read for marks. Don't read for us. Don't read for anyone. So read yourself. This gives the knowledge. Okay. So each and every point you have to follow. Follow the NCERT book. Follow the any competitive book if you have. Then the notes. So and if you have any doubts, that we will come to another one that we will discuss about it. Notes. Now, so mainly in modern physics, if you start with the dual nature of radiation, so numericals. So what type of numerical will come for examinations? Even competitive also. So most of the case there is 2 topics here. Photoelectric effect equation, that is Einstein photoelectric equation, different forms. Then de Broglie equation. So these are the 2 different topics. Okay. So numerical will ask from these 2 topics only. Numericals. So anyway, go anywhere. So all, if you see the exercise of any book, okay, in dual nature, it is completely linked with these topics only. Okay, the 2 photoelectric equation and next de Broglie wavelength equations, different forms. Okay, these are the main concept. So these are the questions. Coming to theory parts. So each and every point is important. Notes, point by point, you have to go through that one. Textbook you can collect it or mark it. Otherwise you can follow the notes. Okay, so competitive point of view, we can discuss that. Okay, then coming to, so what are the numerical point of view? What we have to remember first, what we have to do. That's it. So the numericals in dual nature of radiation. Numericals. To solve the numericals, you should have an idea on this topic first. What are the topics are there, and what are the synopsis? What are the important formulas? Okay. Then let's start with parameters. Okay, just you know that work function, threshold frequency. So they are like the simple structure. So W naught. You know that what is W naught? No need to explain again and again. Work function. W naught is the work function. What is the formula for work function? H nu naught. What is nu naught? Threshold frequency. Otherwise, H is C by lambda naught. This is the equation. Okay. W naught work function, threshold frequency, threshold wavelength. Sometimes they may give the work function of one particular material. What is the maximum wavelength of to show the photo or to eject the electrons? Okay, that means we need to find the lambda naught. They given the work function. Okay, and we should find the lambda naught. Okay, Hc, Planck constant, c, velocity. But work function they will not give in joules because work unit is joule. Here they will use electron volts. What is electron volt? Okay, generally in electronics, how to define the electron volt. If I take one electron, okay, this electron has a charge 1.6 into 10 to the power of minus 19 coulombs. Let us assume that this is one electron here. So by applying of some potential, let us assume that 1 volt of potential applied. So if by applying of 1 volt of potential on this electron, so this charge, okay, due to Q charge is or E charge, small e charge, we applied potential. So due to that potential, this electron will move from one point to other point, some point. So that is the particle, massive particle is doing some work. So that work done by any charge, QV. Here what is Q? Charge of electron. So that's why we are taking. So E is what? 1.6 into 10 to the power of minus 19. V is equals to 1 volt. So that means your work done is equals to 1.6 into 10 to the power of minus 19 into, what is that? 1 volt. Okay. So this is work done. So everything we are taking coulombs SI unit, voltage SI unit. So W is equals 1.6 into 10 to the power of minus 19 joules. And this also we can refer as 1 electron volt. 1 electron volt. The work done by the electron by applying of voltage V. So 1 electron volt equals to 1.6 into 10 to the power of minus 19 joules. Remember that. The smallest unit of work done. Smallest unit of work done. 1.6 into 10 to the power of minus 19 joules. If they given the energy in joules, how to convert into electron volts? Divide it. Divide the work done given in joules, okay, with 1.6 into 10 to the power of minus 19, it will convert into electron volts. Okay, if they given in electron volts, how to convert into joules? If they given 2 electron volts of energy, how to convert this into joules? 2 electron volts. 1 electron volt is nothing but how many joules? This much. So that is 2 into 1.6 into 10 to the power of minus 19. So remember, it's very important for this topic. So 1 electron volt of energy is nothing but 1.6 into 10 to the power of minus 19 joules of energy. So in this chapter, everything, incident energy, that is photon energy, kinetic energy, so work function, they will mention in electron volts. And they may ask the answer in joules, in competitive point most of the cases. So you should know that conversions, how to convert from electron volts to joules, joules to electron, which you already know the conversions in first year only. Okay, so this is one first question. Okay, so second. So already 3 covered: threshold frequency, threshold wavelength, work function. Now coming to Einstein equation, Einstein photoelectric effect equation. What is that Einstein photoelectric equation gives? The maximum kinetic energy of the particles which are ejected from the metal surface in photoelectric emission is equals to incident energy h nu minus work function. Remember it. So work function you can replace with these also. Okay, and so kinetic energy. So this also we can represent. Kinetic energy is equals to, I will write here, h nu is equals to c by lambda. Wavelength, frequency of the incident light is equals to c divided by lambda. That we know that frequency, velocity of light, wavelength relation. Minus. Okay, we mentioned the frequency in terms of wavelength. Here also W naught we mentioned the wavelength term. What is that here? This only now. Here also hc by lambda. This is also one equation. This is also one equation. Okay, this is a main equation. We can modify it into different. Next, instead of kinetic energy, we can write one more term, half mv square. That is half mv square is equals to h nu minus W naught. This is also one. So what is the use of this equation? Sometimes they may ask, what is the maximum velocity of ejected electrons in a photoelectric emission? So we should find V value. So it's all about calculation. Okay, view point of view you have calci, but competitive point of view you don't have that calculator. So they will not allow how to do it. So that's why try to solve now onwards without using calcium. So it will take time initial days, but better to practice now onwards. At least you should know that. So the factors of 1.6 into 10 to the power minus 10. If you divide with 2, if you divide with 3, divide with 5, how it comes. At least you should have an idea about it. Okay. Of mv square. So this is second equation. Got it? So kinetic energy is very, very important. So most of the numericals will come. See, work function also included here. So these are, that's why first one, this also we are including here. This is the main one now. So now W naught also we can mention in terms of H nu naught. See here, instead of W naught you can write any of these two. It's again it's depend upon what the data they given. If they given only wavelengths, convert in terms of wavelength. If they given the frequencies, threshold frequency, incident frequency, then you can go through this one. Okay, this is second one. Clear now? Work function, 1 electron volt equals to 1.6 into 10 to the power minus 99 joules. Make a note of it. Okay, so just I'm revising everything. Kinetic energy, photoelectric effect equation, Einstein photoelectric equation, maximum kinetic energy of ejected electrons is equals this much. So half mv square is equals H2 minus W naught. Okay. Next, third one. Then Millikan experimental verification of the Einstein photoelectric equation by Millikan. In that, what he did, he replaced the kinetic energy of the ejected electrons with EV naught. What is V naught here? Stopping potential. Already know this. Kinetic energy is equals to E naught. Then how the equation will changes now? Instead of kinetic energy, EV naught is equals to incident energy H nu or capital E. Sometimes they will mention incident energy as capital E and work function W naught. This also you can use it. Okay, 1, 2, 3, so fourth equation. Okay, EV naught. E is a charge of electron, V naught is a stopping potential or the negative anode potential applied where photoelectric effect, photoelectric current becomes zero. Got it now? Stopping potential definition. H nu is what? Incident energy, light, frequency, Planck constant. So incident light energy minus work function. Its work function completely depends upon the metal what we taken or metal of the incident surface. Okay, EV naught is equals to H2 minus W naught. Again, you can convert nu in terms of lambda, W naught in terms of lambda, that already you know. Same topic repeat. By replacing of different terms, the equation also changes. Okay, this is the third one. Now coming to the last one, de Broglie wavelength. So I'll write in one form, de Broglie wavelength lambda is equals to first form H by P. H by P. H is what? Planck constant. P is the momentum of the matter particles. Otherwise, H by root over. So the momentum and kinetic energy relation 2m into kinetic energy of the particles. First form, already know I given this information in notes, the previous classes. H by P, this one. Okay, again this kinetic energy replaced with what? EV. So because kinetic energy is equals to EV dot this kinetic energy is equals to E into V. V is what? Accelerated potential for that electron or the particles. So m is the mass of that particle, E is the charge of electrons or charge. If it is protons, proton and electron both have the same charge. So 1.6 into 10 to the power minus 19 and m is what? Mass. If it is electron 9.1 into minus 10 to the power minus 31. If it is proton 1.67 into 10 to the power minus 27. So that is, you can take it. Okay. So V is what? Accelerated potential. So this, so work function is the first equation, kinetic energy, okay, of photoelectric effect case, second one and the third one, fourth one, fifth one, sixth one, including of 3. Okay. So actually one short form also given, lambda is equals to 12.27 by root V. So lambda p value and lambda alpha particle something they given. Okay, deuteron 1.010, alpha particle 0.202. So the data given in last class. So this is very helpful for the numericals. Okay, next one coming to what only this is this enough for competitive? So I would say definitely it is no, because we can't guess that every time numerical from this chapter. Sometimes they may ask some relations, so linked topics, so that we will discuss in competitive point of view. Let's discuss about PU here. So PU point of view, each and every line or each and every case is very important for it. Okay, so that's why better to have an idea on theory. Okay, better to have an idea on theory. So let's this is complete topic now. Just revise it and what the assignment given, just to go through that one. Okay, then immediately we'll go to the next topic and for next session. So next topic will inform in group. Okay, so be prepared, but you should finish the assignment. If you keeping on pending of assignments, very difficult. Please finish the assignment. Okay.